My name's Guido. This is my colleague Callum at the back of the room there. We're working here at Trobe University, and we're doing something called the Freely Accessible Remote Laboratories. It just stands for FAR Labs. And so that's it there. And the idea is that for experiments like this, the diffraction experiment, or for other types of experiments, whether your school has the appropriate equipment or the appropriate training or the appropriate licenses in terms of radioactivity shouldn't impact on your ability to do an experiment like this. So at a university where we have a bit more access to these sorts of pieces of equipment, what we're doing is we're going to set up this equipment. It's going to be dedicated for high schools, your high school and other high schools, and all that will be required sort of on your end is to go to a website, make a booking, log in, and then you can do one of a number of experiments. At the moment we've got 3, but we're going to add a few more. And that's with actual dedicated equipment. So for example, you guys are Year 11 students. Are any of you studying physics?
Yeah.
You're all studying physics. Okay. So it's August now, so I'm guessing that's Unit 3, but in one of the units you would have studied radioactivity, right? Is that right? So you would have learned about the structure of the nucleus, why some nuclei decay, and when it decays, it emits various types of radiation, either alpha, beta, gamma particles, and then you get the various sort of daughter nuclei and so on. Okay, so let's just click on this one. Did you guys do any experiments with radioactive sources? No, okay. So the reason for that is that some radioactive sources require a license and proper training to use because they're quite hot, they're quite active. Other ones don't, but even if they don't require a license, so literally I could just go and buy some off the internet, they're actually pretty expensive. So we set up this one, and so what I mean is maybe a school can't spend $5,000 on a set of radioactive sources. So we've set this experiment up, and what you see is basically 2 kind of carousels. One has radioactive sources, these 4 here. The other one has different absorbers. So for example, there's plastic, 2 pieces of aluminium, and a piece of lead, and just a simple Geiger counter. And this is actually happening in real time. This experiment is housed about 500 meters away. And there's various things we can study in this one. So at the moment, I've got it on the alpha source, and alpha particles are big and heavy, and they get absorbed very easily. So for example, I want to put another slide with just a piece of tissue paper, because even tissue will stop alpha particles. So if I just click plastic, and if the lag isn't too debilitating, it's on the wireless connection. So that video feed should be a little bit smoother, but nevertheless, you get the idea. And we'll see the counts should just drop off straight away. It's integrating at the moment. And it's decreasing. But if I leave the plastic absorber in the way and change to the gamma source, gamma essentially are high energy photons. So they're even higher energy than X-rays, even shorter wavelength than X-rays. I'll just put that in the way, and they'll punch straight through the plastic, and we'll get an increase in counts again. And there it goes. So all this is actual equipment. It's available to use. While we are developing the equipment and sort of this technical side and the website and all that sort of thing, we're going to get in contact with yourself, for example, and high school teachers around in order to develop the content. Because we're good at doing this sort of stuff, but I'm sure the teachers know exactly how to pitch it to you guys, how to make a simple experiment that would last, say, 50 minutes for a period, or 90 minutes if you guys have a double period or something like that. And just have sort of a closed package task for you guys to do, learn about radiation, actually use real equipment, and therefore it's a bit more interactive that way, instead of just reading about radiation through a textbook. So this is the one we have for radioactivity. We've got a couple more. I'll just go back. We have a solar hot water heater, which is actually currently being commissioned between La Trobe and its inventor, who I think is in Bendigo, but maybe they said Ballarat. So we're actually collecting data for this, and part of, if you guys get involved, you guys will actually help us collect data for that. We also have one with the synchrotron, which is similar to this experiment, but using a synchrotron beam. So if I log in here, you guys can do this as well, or you will be able to do this. So you can make a booking, for example. This is us here, the 21st. These ones are all gone because they're sort of this morning, but this one's still open, so I can click there. You guys are year 11, so let's do that. And okay, so it tells me, so the current booking is then. If I start my session there, I'm greeted with something like this. At the moment, the synchrotron beam is unavailable because they do regular maintenance, just like servicing your car, but this is a far more precise instrument, so the maintenance are a bit more often. But nevertheless, they're doing it now, so that's not available. So we have a switch here, and it's currently on laser light. The booking system you just saw will be incorporated with the maintenance schedule, so you're not actually, for the most part, you're not able to book during the maintenance session. If we're connected to the synchrotron, we want you to use the synchrotron, not the laser pointer. But for the purposes of this demonstration, we've just got laser light. And so in a, well, sorry, I was about to say in a similar way, not in a similar way, in exactly the same way as diffraction occurs here. We've got a series of double slits. So you'll learn this if you continue physics, if you do optics, for example, and you get a diffraction pattern downstream of the aperture. And with a bit of maths, which is not important for this session, but we can work out the fringe spacing and work out various details of that aperture. We have several different ones, and I'm not going to tell you what they are. And if you do the exercise, you won't know what they are. Your job will be to calculate what the apertures are. But for example, we can switch between them. This may take just a few seconds. And then you've got several different things. You've got a task to do. In the final version, you'll be using synchrotron beam. And you can do a 50-minute or a 90-minute exercise using actual equipment that you might not otherwise be able to use. So for example, I've changed the aperture and the diffraction pattern completely changes because it's different slit separation and details like that. So we're hoping that you guys would be interested in something like this. Over the next sort of month, we're going to be developing it more and polishing it, making student notes available, making teachers' notes available. For the students, all you guys really have to do is have access to a relatively decent computer and an internet connection. All this will be available also to be used on an iPad, for example. So being sick is no longer an excuse. I'm sorry about that. You can do it from home. And our job is just to provide the notes and that sort of thing. For the teachers' side, we'll be getting in contact with you guys to help us develop the actual content, because you guys know best how to pitch it to the correct level. There's a risk that if I were to develop it, I might write some differential equations or something. It's been a long time since I was in high school, and I just missed the ball completely. So that's what we're trying to do. It's called the Freely Accessible Remote Laboratories, just stands for FAR Labs. And we hope to roll it out to schools around Victoria and Australia, and we hope that when we do, you guys would be willing to give it a go for us. So that's all from me. But if you've got any questions, I'd be happy to answer them.
Do you know what sort of patterns those slits have?
So,
you know how it says A, B, C, and D? Are they they're obviously different because the diffraction patterns are different?
Yeah, that's right.
So do you know?
Do I know what they are?
Yeah.
Yep. I do.
Yeah. Oh, okay.
So, what you can't, right off the top of my head, I can't make a calculation about, so for example, there are two things. You have, let's say you have two slits, right? So this is like an opposite slit. Let's say this is all covered, and these things are just free air, just sort of engraved in a piece of metal. What you see here will depend on two things, really. It'll depend on how far apart they are from each other, And it also depends on how big the individual ones are. So that would look completely different if the slits were like that, if they were thinner. It would also look different if we did that and just moved them further apart. So just based on those two things, the width of the individual ones and how close or how far apart they are, will completely, well, not completely, the overall structure will look similar, but it will change the tiny details. And that's in fact what this experiment is about. Yep.
Besides the radioactivity and the diffraction, what other experiments do you plan from the pilot?
So at the moment, let me just go back. Finish. At the moment, we've got a solar hot water one. I don't know. We have a solar hot water one, which is currently running. So if you did this one, you'd see something like this. If I just click a few, it has 20 temperature sensors in it because it's a big tank, and we have temperature sensors sort of all throughout the tank. And we want to measure essentially how well the system heats up during the day and how well it sort of retains that heat during the night. So if I change the date range to, let's do a couple of days. So this is from the 19th, which was Monday, to now. Data. We see something like this. And, okay, so temperature's increasing. This is the day, right? But you notice that the temperature, it increases in energy, in temperature, quite well here. And it actually stores the energy relatively well here. It's not cooling down very much at all. It's well insulated. And then it sort of happens again, and so on. And what we want is, well, a good system would be something that stays within your temperature range. So for a hot shower, it's about 50 degrees is what you want. Certainly not 80 degrees, that's way too hot. So for a hot shower, you want about 50 degrees, and you want that temperature relatively stable. So no matter what time you get home, if you had a bad day or whatever, you can have a shower, it's not going to be cold. Even if you have a shower here, for example, well, this is 26 degrees. So that's not great, but it's winter, and this is a test case. This is actually being invented, and the patents are out in the process of being developed, and we need data from it at the moment.
I was going to say, so that's actual data from the experiment that people have made.
Yeah.
Like heat up our water from the sun.
Yeah. No, this is currently running on the roof. Just that way, maybe 500 meters away. It's currently running.
What are the different sensors referred to as in T1, T9?
So it's a big drum. I think it's about 200 liters. So it's about sort of that tall and maybe this wide. And there are 20 temperature sensors throughout it. So we want to measure the temperature gradient with height and also with distance there. So they're sort of evenly spaced throughout it. The reason for that is that it has a self-regulating temperature stability. So if there is a temperature gradient throughout it, which there may be, maybe not, but there might be, it will move the water around passively in order to get the smoothest temperature gradient possible. And so we put the sensors in to see if it was in fact doing that. Yeah. So those three are the ones we have at the moment, the radiation, solar hot water, and the synchrotron one. We're hoping to add at least one more to do with X-ray tomography, which is a process of getting a three-dimensional image of something. And we'd have several different samples for you guys, and you guys can pick one. You won't know what it is at first, but once you do the experiment, you'll see, oh wow, that's an insect or something else. So yeah.
Do you know roughly how much it will cost our schools?
This will cost your schools somewhere between $0 and 30 cents. So we've been, no, it's a legitimate question because in fact, that's exactly why we did this, because we understand the schools don't have resources for, say, a solar hot water system or access to a synchrotron beam. So we applied for a grant from the government. There were a few different grants. We were lucky enough to get the grant. And in there is the funds to pay for people like myself and Callum to develop this. We have the equipment already here. In fact, we've got pieces of high-tech equipment in the basement that are currently being used for science. They're not used 24 hours a day, so when they're not used, why can't we develop a simple program or a simple experiment to sort of farm out to you guys? It will cost you in terms of time if you're happy to talk with our teacher liaison officer who's developing the appropriate notes for these experiments. We'd love to get your input with that. But in terms of once it's developed, all you'll need is an internet connection, a relatively modern computer, and any kind of internet browser. Hopefully not Internet Explorer, but that will work. But Chrome and Firefox are significantly better, but it will work with Internet Explorer. Any normal internet browser will work. Do you guys have relatively modern computers connected to the internet?
i3s.
Sorry?
Intel i3.
i3. Perfect. That's more than enough. Yeah.
We've got Explorer.
And you have Explorer? Okay, well, we'll work with it.
Okay. Thanks, Peter.